All right, so today we're going to continue on with our Unit 1, and we're going to be moving on to Chapter 2 now. Our focus will be on measures of location, measures of spread, and interpreting data and distributions associated with those measures. Our motivating example today comes from the fact that we're going to focus on measures of location today, going both forwards and backwards. So this data is provided to us courtesy of a retired professor in the Department of Mathematics and Statistics. His name is Harold Bennett. And he generously provided this data because it was critical for him to recognize something going on during this particular semester. This semester was the fall of 2020, which many of you will remember to be the first semester fully contained by the coronavirus pandemic. And for that fall semester, the vast majority of courses at Texas Tech were moved online, including most of those in the Department of Mathematics and Statistics. Many professors, obviously, would have to proctor exams online, say with Proctorio, or just give them out as assignments. If you did choose the latter, there would be a risk of potential cheating. And for the first exam, the average and the median were roughly equivalent. We'll get into more formal definitions of those in a moment, but most of you are probably at least conceptually familiar with what the average and the median are. The median being the data point right in the middle, if you order them from lowest to greatest, and the mean being the average of all the data points. Usually, when it comes to grades, you expect the average and the median to be not too far removed from each other, i.e. a bell curve, for example. On the Unit 2, or midterm exam number 2, for his differential equations course, the average stayed about the same. The median went up by a few points. Maybe that's something that could raise an eyebrow, but otherwise not too out of the ordinary. However, Hal noticed that there were quite a few students who had the exact same submissions, exact same grades, and he noticed that those problems where they had the same answers, not all the problems, but ones where there were answers online, were uploaded to a website called Chegg. And so here's what Hal tried to do. For his midterm exam number 3, he worded the problems so that it would be really easy for people who were genuinely doing the work, but would be completely impossible to anybody on Chegg. On this midterm exam number 3, we can see the average and the median were a staggering 14 points apart. As you'll see later in the course, that type of a difference does not occur by random chance. And indeed, here we have a display of the grades from that midterm exam number 3, again courtesy of Hal himself without violating FERPA, here. And this display, you're familiar with it from the previous chapter. We notice it's not unimodal. We have two peaks. We have a peak in the 80s and a peak in the 60s. When you have an exam distribution with two different peaks, that is a very heavy indication that something nefarious is going on. Usually, the higher peak is where the cheaters are, but remember, in this case, I said that Hal designed the test so that it would be really easy for people who weren't cheating, but really hard for those that tried to use Chegg. In fact, this peak, now not quite as large of a peak, but nonetheless a peak, in the 60s was in fact predominantly cheaters. Not all of them, but a very high proportion of the known cheaters. In fact, as you can see, and again, you have a little bit of variance, but for the most part, we had a much higher proportion up in here, as would have been indicated by the structuring of the test. The reason why I point this out is because you never would have been able to figure this out, unless you happened to stumble upon it by sheer chance, without looking at the increasing and increasing divergences between the average and the median, these measures of location. These numbers are oftentimes some of the first indicators that you're dealing with something interesting. And whether you're working in animal sciences or working in business, this type of data can be extraordinarily useful, not just from an oversight perspective, say when trying to find out corruption, but when identifying differences between populations, such as to distinguish from placebo effects. So, in this lecture, we are going to focus on quantifying these measures of location, going through some practice problems, and then using them logically to show how we can glean a lot of information just from a few measures of location. So, we're going to start with our four simplest ones. We have what's called the mean, and that is equal to the sum of the data values divided by the number of data values, or our size. We denote the size by n, our sample size, or maybe population size. And we have this is the Greek letter sigma. This thing right here is the Greek, capital letter sigma. And it means sum of this stuff. So for example, if I put the sum of I, and I starts from 0 and goes to 10, then this means the sum, let's make it 1, just so it's easier. This means the sum of the first 10 positive numbers. So that would be 1 plus 2 plus 3 plus 4 plus blah, 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 all the way to 9 and 10. This Greek letter sigma makes it much easier to write things down on your formula sheet. We're going to be using this notation a lot, but just keyword, sigma means sum of whatever these are. So in this case, the sigma sum of xi just means the data values. You might say, what does this I mean? I just means whatever data value it is. So all the data values denote xi. So xi could be the first, the second, the third, the fourth, so on and so forth. Technically, if you wanted to, you could write down I equals 1 to n for completeness. So therefore, the first data value, the second, the third, the fourth, so on and so forth, up till the nth. But simply using sigma itself is a shorthand for all of them. Our mode is the most frequent data point. And we can have multiple modes. But there must be at least 2 data points for one of them to be the mode. So if our data points are 1, 2, 3, 4, and 5, there's no mode. If, say, they're 1, 3, 3, 3, and 5, then our mode is 3. But if they are 1, 2, 2, 3, and 3, then we'd have 2 modes, 2 and 3. In this case, if you said a mode is 3, you're technically not wrong because you're specifying one of the 2 modes. Next up, we have the median. And for this, you don't technically have to do it, but I strongly recommend doing so because it will help for the range and also make it less likely that you'll make a mistake. What you should do, take your data points and sort them in ascending order. If you have a stupidly large number of data points, then at that point you'll be using Excel. If we have an odd number of data points, then our median is going to be the data point right in the middle. And if we have an even number of data points, then the median will be halfway between the 2 data points in the middle. So for example, if our data points are 1, 2, 3, 4, and 5, the middle one is 3, so the median would be 3. But if our data point included a 6, we'll take the halfway point between 3 and 4, which would be 3.5. This does mean there is a chance that your median will not be any of your data points. Finally, we have the range, which is equal to the largest data value minus the smallest data value. So again, if we had 1, 2, 3, 4, 5, 6, the range would be 6 minus 1, which would be 5. So we'll go over a few very elementary examples just so you can get familiar with these computations. I will note, though, that when I test you on these, I will primarily focus on concepts involving these, because anyone who has Microsoft Excel can very easily compute these 4. However, if they don't understand the concepts, they can't work backwards nor comprehend what they're doing. So again, we'll start with a few very simple computational examples. If you want to pause and do these 3, so examples 1, 2, and 3, you're more than welcome to go right ahead. But otherwise, I'm going to go ahead and go over the answers. First one, to find the mean, that's straightforward. Our mean, which I'm going to denote by B bar. You might say, wait, what is this bar? What the hell does this mean? So we have what's called X bar and the Greek letter mu. Well, not mu, but mu. So M-U. That's how it's spelled if you want to spell it in English. We say mu. If you want to pronounce it like a cat, sure, whatever. Mu is for a population. And X bar is for a sample. So for example, if I took 10 of you as for your Unit 1 test scores, that would be a sample of all the test scores, and we would denote that sample mean with X bar. If I took all of you, the whole class-wide average, that's now the population, so it would be the Greek letter mu. Sometimes, if it's convenient to switch the X to a different letter by virtue of the label itself, then we could do so. So for example, since these are grades, if we were referring to just these guys, we could call that a G bar. G standing for grades, but again, the bar still indicating it's a sample average. And of course, we took all of these. Again, you can call it mu again. But anyways, that notation out of the way. Our mean, in this case, will be 9.2 plus 6.4 plus 10.5 plus 8.1 plus 7.5 divided by our sample size of 5. And this, you throw it straight into the calculator, and you will get 8 point. Oh, that does not look like a 4. There we go. You'll get 8.4. On the test, you'll be allowed to use a regular, boring scientific calculator. You won't be allowed to use a graphing calculator because oftentimes those will just straight up do it for you. But Proctorio on every test will give you a scientific calculator. And I apologize, this is 7.8. I cannot read. There we go. Sorry about that. So 8.4. Our median, let's sort the data points. Our lowest data point is 6.4. So I'll just put a dash through that. Our next lowest is 7.8. You don't have to do this. I do it visually for those who are visual learners. Then we have 8.1. Next up we have 9.2. And then we have 10.5. Our median will be the one in the middle, which is 8.1. That's it. Not much else to it. It really does not get more complicated than that in terms of raw computations. It's when you go backwards or you're dealing with displays and tables where it gets more interesting, which we'll get to that in a moment. Example number 2. In this case, we'll just call it X bar. This is equal to the sum of our data points. So 15 plus 3 plus 46 plus 623 plus 126 plus 64. And this we divide by our sample size of 6, which, if we pull up our calculator, gives us an x bar of 146.166 repeating. For web work, you round that to 3 decimal places. We can call it 146.167. Our median, let's sort data points again. Our lowest one is 3. Then we have 15. Next up, 46. Then 64. Then 126. And then 623. In this case, since we have an even number of data points, our median is going to be equal to the halfway point of these two. Halfway point, 46 plus 64 over 2, not 22, good lord, just 2, is equal to 55, which is our median. I'll tell you, it would have been a bit embarrassing if I couldn't sort that correctly. And number 3, we want the mode. First of all, our only candidates are ones where we have at least 2 data values. So that would be the 0s, the 2s, and the 3s. So if you say anything else besides those, you might want to check yourself into a mental facility. But the mode is the one where we have the most number of data points. In this case, we have 5 3s and just 2 0s and 2 2s. So therefore, our mode is 3. For the sake of argument, if those 3s weren't there, then we would have had 2 modes of 0 and 2. Now, before I continue, before we go on to categorical medians and modes, are there any questions? Yes. The notation. So here, you can call it, the technical term is overline, but we just call it bar. So the letter and then bar. This letter and then bar denotes the sample average. So it could be A bar, B bar, C bar, doesn't matter. Usually we use the X bar because in most cases X is our default because X being the independent variable, our input. So we usually default to X bar. Occasionally, if the data points are labeled with something that's really convenient, B for birth, then I can say B bar. Or you want to say W bar, that's fine too. Point being, bar corresponds to sample average, mu itself corresponds to the population. Yes. The sigma. So here again, that sigma is the Greek letter sigma. It just means sum of whatever's after it. So I could say sum of n, which means, or that ni, whatever. This means the sum of whatever this is. So for example, we could say sum of xi minus 1. That would mean the sum of each data point minus 1. Do that for all of them. That sum, that sigma means sum. All right. Now we're going to move on to categorical modes, categorical medians. So let's come back to this display. If I asked you, what is the mode, or what was the mode exam score versus what was the mode exam letter grade. So here, standard grading scale. You might think, oh, this is easy. The mode is 85 and the mode letter grade is B. You would only be right on one count. How many of you think that the one that is correct was the mode exam score? Okay, how many think the mode that was correct would have been the letter grade? And how many of you are just confused as hell? Okay, that makes sense. So here, think of it this way. What was the mode exam letter grade? Well, think of it this way. This is an A, that's a B, that's a C, that's a D, and these are Fs. So we would have 15 Fs, 13 plus 12. We'd have 21 Ds, 16 Cs, 33 Bs, and 23 As. So the mode letter grade, exam letter grade, is the same thing as saying what letter grade was the most common. We can answer that. A B. Now let's go to the other one. What was the mode exam score? You don't know. Now you might say, what? That makes no sense. It's obviously in the 80s. Says who? What if these 21 scores in the D range were all 65s? Let's make that clear. What if these were all 65s and these we had 1781s and we had, say, 1687s? Well, then in that case, the mode would not be in the 80s. Conversely, if all 33 of those B scores were 85s and all 21 of these D scores were 65s, then the mode would be 85. Because we don't have the actual scores, we can't get the mode exam score from this display. So, because we don't have the raw scores from this display, we can't find the mode exam score. However, with the secondary one, a letter grade is a category. And so, because this is the equivalent of asking for the most common category, this display is sufficient to find that mode letter grade. And the median is much the same way. With the median, here we're told it's an 80, but if I showed you this alone and I asked you what's the median, you're squat out of luck. You don't know what the median is. You have no way of knowing whatsoever what the median midterm examiner 3 grade is without it being provided to you. If this whole thing, well, let's get rid of this. If that was gone, you would have no way of knowing what the median exam score was. You could, though, get an idea for the median letter grade. Here's why. So, think of it this way. We have our horrible people and then the hundreds. So once we get to 50 people, we would have 3. I'm sorry, when we get to a score of a 50, we have 3 people. 3 people have a 50 or lower. So I'll put less than or equal to. 12 plus 3, so 15 people, say right here, have a 60 or lower. And here, 21 plus 15, so 36 people. 36 people have a 70 or lower. 16 plus 36. 52. 52 people have an 80 or lower. 52 plus 33 would be 85. This is not strictly proportional, just to give you an idea. 85 people had a 90 or lower. And then finally we add the other 23. Everybody had 100 or lower. So this is a cumulative frequency distribution. Again, we talked about this back in chapter 1. What we've done here is create a cumulative frequency distribution of these exam scores by 10-point increments. So let's think of it this way. How many exam scores do we have? Well, 3 plus 12 plus 21 plus 16 plus 33 plus 23. We have a total of 108 exam scores. So the median is going to be between the 54th and 55th data points. So let me put 54th and 55th data points. So think of it this way. Look at 52. 52 students, so I'm going to change the color, it's easier to see. 52 students out of 108 got an 80 or lower. So more than half the class got above an 80. Okay? Now, let's go to our next. So if we put it this way, less than or equal to half of the class. I'm sorry, less. Less than half of the class. Just want to make it very clear, easy to see. Less than half the class got below an 80. Here, it doesn't matter, it's just the boundaries, same idea. Now, let's change to orange. 85 students got below a 90. 85 out of 108 is far more than half of the class. So, more than half of the class. Let's make that H a little bit clearer. Got below a 90. So think about it this way. If we ordered all of these exam scores from 0 to 100, if we chose 80, less than half of the exam scores would be below an 80. If we chose 90, more than half of the exam scores would be below a 90. What that means is the median has to be somewhere from 80 to 90. So, the median must be from 80 to 90. Inclusive of 80, exclusive of 90, because of how we have defined it. Indeed, you'll notice this 80 with inclusive happens to include the median. So we can't know for sure, just from this, what the median numerical score was, but we can get a range for it. But look at this. If the median must be from an 80 inclusive to a 90 exclusive, that's a B. No matter what number that is, it must be a B. Therefore, we can conclude the median letter grade has to be a B. So with the mode and the median, same idea. If we're just given, say, a histogram, we can find the categorical mode and the categorical median, but not the numerical mode or the numerical median. So I'll write that out up here for you. Given a display, like in the motivating example, we can find the categorical mode and categorical median, but cannot find the numerical mode and numerical median, in this case, off of that display alone. And this is important. I'll ask you a lot about it. Now, I understand that this may feel like a lot to take in, and oftentimes in situations like these, it can be helpful to go over a practice problem. That's what we're going to do. And remember, as long as you can order the data, that's all that matters. You could have, again, letter grades can be ordered. A, B, C, D, F. Even though Texas Tech doesn't make a distinction between a 92 and a 98, doesn't mean we still can't order the letter grades. So, let me give you an example to work through. So here we've got a pie chart. It's another display. First, I want you to find the mode for this pie chart. And I also want to find the median. In this case, something to point out is that these are categorical. So if you want to take a moment to try both these, go ahead and pause and try. Something I do want to point out, in pretty much every case, finding the mode category is much easier than the median category. All right, in this case, our mode is the most common. Here, that's our 46% sophomores, so the mode category, Lord have mercy, that does not look like a T. The mode category is sophomore. Now, what about the median? Well, in this case, a very nice English way of explaining all that shit we did up here would be this. Start from the low end, keep adding categories in order until one of them puts you over 50%. And the one that puts you over 50% is the median category. In fact, I'll write that down for you, or I'll type it out. That's a lot of words. All right, there we go. Type that out. I'm going to show that in action. I'm going to show how no matter which end you go from here, you're going to get the same median category. Let's start from the lower end, our 10% freshmen. If we start from the lower end, 10%, that's nowhere close to 50. It's not going to be the freshmen. Now let's add the sophomores. So sophomores plus the freshmen plus the sophomores, 10 plus 46 is equal to 56. That means a majority of the students are freshmen or sophomores. So we know one of these two has to be the median. Which one? The sophomores, because that's what put us over the top. So, going from the lower end tells us sophomores. But let's now do it from the other end. The upper end would be seniors. 14%. That ain't 50. Let's now add the juniors, one step below. 14 plus 30, that's 44. Still not a majority. It's not going to be the juniors. Let's now add our next category. Here would be the sophomores. So 14 for the seniors, 30 for the juniors, 46 for the sophomores is 90. This puts us over 50. So the category that put us over was the 46%. Notice in both cases, the 46 is what put us over. So, sophomores are the median category. Now, if I'd asked you, what is the mode age, you have no way of knowing. Because sophomores can be different ages. People are born at different points of the year. You don't have the ages yourself. So if I asked you what is the mode age or the median age, you wouldn't have enough information. So I'll write that down. Side note, if I had asked you for the mode age, so I'll write numerical age, or the median numerical age, you would not have enough information to answer. And indeed, that'll pop. These will both pop up on the test. All right. So that is that for the most part for our 4 measures of location, the most common ones for now. But let's move on to a one that actually shows up in college all the time, and that is called the weighted mean. The weighted mean is equal to the sum of the weights times their associated values divided by the sum of the weights. Now you might be asking, what the hell is going on here? Well, the sigmas, those are still sums. So the denominator should make sense, the sum of the weights. Usually this adds up to 1. Now the numerator might say, what in God's name is going on up there? Well, here this parentheses means that you do this before you start adding things up. Wi is the weight, xi is the data point, so you can think of it as the product of each weight with its data point. So for example, suppose that you had a professor who is special. And your whole grade was determined by 2 midterm exams and a final exam. The 2 midterms were 25% each, and the final exam was 50%. If you have a professor who's doing this to you, they're probably tenured. Anyways, so in this case, this would be our first weight, W1. That would be our second weight, W2, and that would be our third weight, W3. And these compose our weights. So W1, W2, W3 for any given Wi. And your exam scores are the XIs corresponding to those weights. So if your exam scores were, say, 40, 50, and 60, then your X1 would be 40. So you'd have 25% times 40. Your X2 would be 50. So then you'd have 50 times 25%. And then your X3 would be 60. So 60 times 50%. You do those products and you add them all together. So your weighted grade would be 25% times 40 plus 25% times 50 plus 50% times 60. This is how grades are computed. The weighted mean is how we compute your grades. That's how we do it in this course. So here, I want to show, though, a connection between the weighted mean and the mean. The mean itself is, in fact, a specification of the weighted mean, and we're going to do a practice problem to help you understand this. So here we got this guy, Crispy Bacon. He's a complete and total idiot, and he's scoring 20s and 30s and 40s on the homework sets. God, Lord help him. So I want you to take a moment, do both of these. First, notice since all of these scores are weighted the same, you can use the regular mean formula. What I want you to do is use both so that you can see how both are related to each other, and that, of course, you get the same answer for each. So go ahead, take a moment, and work on it. All right. So here we're going to use the weighted mean. In this case, we have 25% weights each. So our WIs are all going to be 0.25. So our first weight for the Unit 1 homework set is 0.25. And he scored a 25% because he's a complete and total idiot. That or he didn't do it, probably both. Our next one also has a weight of 25%. And this time he did a little bit better, still horrible, and got a 30%. The third homework set also has a weight of 0.25. And this time he scores a 40. And the last one has a weight of 0.25. And he scores a 45. In this case, to show you the connection, these are our WIs. And these are the XIs. We divide it by the sum of the weights, so 0.25 plus 0.25 plus 0.25 plus 0.25. This whole thing is equal to 1, so it's just equal to the numerator. And this is going to come out to be a 35%. Anyway, we're going to throw a percent on, doesn't matter. It's a 35. Now let's use the standard mean formula. That's going to be equal to 25 plus 30 plus 40 plus 45, the sum of our XIs, divided by our size of 4. In this case, it's now the population. And that is a 35. This is the mean because it's all of his scores. Notice we get a 35 both times. That's good. But I want to point out something else. Notice the connection. If everything is weighted equally, then either they're going to add up to 1, or notice, cancel. We're going to cancel things out, and we're going to be left, think of it this way. We can factor out the 0.25s. So we'd have 0.25 in the numerator. Again, we factor out all these 0.25s. So 25 plus 30 plus 40 plus 45. In the denominator, we factor out these 0.25s. So we should have 1 plus 1 plus 1 plus 1. Lo and behold, these 0.25s cancel out, and we're left with part B. This is why the standard mean formula is really just a specification of the weighted mean formula, because everything's weighted the same. So there you go. Now you see this. You see the connection. Anyways, any questions about the weighted mean? All right. What we're finally going to move on to is working backwards. Now that we have these measures of location, range is kind of sort of a measure of spread, but it's simple enough that we might as well group it here. We can go backwards. Given our measures of location, we can figure out the data points given that we have a sufficient amount of information. You might ask yourself, how, what? Please explain. With logic. Think of it this way. I'm going to do it just by straight up showing you a practice problem, because here the process would be a little bit arbitrary. Let's go through a hard example. We got 5 data points. We're going to assume they're integers. Let's call these data points A, B, C, D, and E. Okay? Let's order them. Suppose that A is the lowest, B is the second lowest, so on and so forth, up to E being the highest. You might say, why? Why does that matter? Technically doesn't for now, but it'll matter when we do the median. So let's suppose that these are ordered. Then A is less than or equal to B. Not less than or equal to, because 2 could be the same. B is less than or equal to C is less than or equal to D, and D is less than or equal to E. So, now that we have this, let's start looking at what we have. The mean, the median, and the range are all 7. The median is equal to the middle data point. Since we have an odd number of data points, C is going to be the median. And we're told the median is 7, therefore C must be 7. Let's move on to our next one, the mode. The mode is 10. Since we have a mode, that means at least 2 of the data points have to be the mode. So we've got to have at least 2 10s. Well, last I checked, 10 was not less than or equal to 7, which means D and E both have to be 10. For those of you that have played Sudoku before, it might kind of sort of feel like that. You know, one of them logic puzzles. This is kind of sort of the same way. It's a hybrid of math and logic. So we've got the mode, we've got the median, so let's actually replace those with red. Let's now look at the range. The range is equal to the largest minus the smallest. So our range is equal to the largest, in this case E, minus the smallest, which is A. Well, we know the range is 7. We know that E is 10. So A has to be 3. Now that we're done with the range, all we have left is the mean, and we have 1 data point. Now here is where I'm going to introduce you to what's known as the alternate form of the mean formula. And the alternate form is that the number of data points times the mean must be equal to the sum of data points. We can just put x at this point. Doesn't matter whether we use xi or x. Same damn thing. Why is that correct? Well, we come down here, we just multiply the n. That's it. So still holds true. You might ask, okay, you know, it looks nicer, but explain to me how this is useful. Here's how it's useful. Look at it here. We have 5 data points. And our mean is 7. This has to be equal to the sum of the data points. Sum of our x is A plus B plus C plus D plus E. Well, that's 35. We know what A is. That's 3. We don't know B. We know that C is 7, D is 10, and E is 10. This is straightforward. We can find B now. 35, 3 plus 7 is 10, plus 10 plus 10 is 30, is equal to 30 plus B. Therefore, B must be 5. By using the alternate form of the mean formula, we can get our last data point. Indeed, the alternate form of the mean formula is so useful that you don't even have to know what all the data points are to get something out of it. There's a web work problem that has to do with scores by gender, and you're going to use the alternate form of the mean formula to solve that web work problem, again, to show the applications of it. So now what I'm going to do is I will do another practice one. I'm going to do the third one. and then you're going to do the last one. But if you wanted to go and do this one, you can go and do it right now. So here, we have 5 data points with the following properties. We have modes at 4 and 7, and the mean is 6. All data are integers. What are the 5 data points? Well, again, we'll start like before. We have A is less than or equal to B, is less than or equal to C, less than or equal to D, less than or equal to E. We don't have a median. Let's go to the mode. Well, we have modes at 4 and 7. So, we know that 4 of our data points are going to be 4, 4, 7, and 7. It's reasonable to assume that this guy is going to be 4, and that this guy is going to be 7. However, C could be 5 or 6. It could be something else. Because the mean is 6, that strongly implies that our C could be something else. But we're not going to make any assumptions. We just know that 4, 4, 7, and 7 are our 4 of our data points. It's reasonable to assume, given that the mean is closer to the upper mode than the lower mode, that A and B are going to be 4. It's reasonable to assume that D is going to be 7. C could be 7. E could be 7. Doesn't matter. Because we got 4 of the 5 data points and we have the mean. So, guess what? The number of data points, 5, times our mean of 6, has to be equal to the sum of our data points. So 4, 4, 7, and 7. The last one you can call X. Doesn't matter. I'm just going to call it E. In part because I know what the answer is. So 5 by 6 is 30. 4 plus 4 is 8. Plus 7, 15. Plus the other 7, 22. 22 plus E. So therefore, E is equal to 8. And so we know our data points are 4, 4, 7, 7, and 8. In these cases, notice we had no range. We had no median. We didn't even know if the last data point was going to be C or E. Doesn't matter. We can still use logic. So now we have this last one here. This one can be a bit of a tricky one. If you want to go ahead and work on it, you can. But otherwise, I'll work through it. I'll give you a little hint. There's more than one mode. I just didn't give you the other one. But you can use logic to figure out the data point. So here's what we've got. We have A is less than or equal to B, less than or equal to C, less than or equal to D, less than or equal to E. Let's start with the median. The median is 6. Okay, and we have a mode of 3. Last I checked, 3 was less than or equal to 6. So that means A and B also have to be 3. Now, at this point, you might say, we're screwed. We have the mean, but we're missing 2 data points. You done pranked us. No, I didn't. We're going to use some logic here. So, here's what we know. We got 5 data points. Our mean is 5. And that has to be equal to A plus B plus C plus D plus E. So 3 plus 3 plus 6 plus D plus E. So 25 is equal to 3 plus 3 is 6, plus 6 is 12, plus D plus E. Therefore, 13 is equal to D plus E. Now you might say, see, you screwed us. What the hell do we do? Here's what we do. All data points are integers. What does that mean? D and E have to add up to 13, and they got to be integers. So you can't have 2 6.5s, because those aren't integers. Let's suppose that, so here I'll type it down. And here we'll use the positive ones. our possibilities are, or some of our possibilities are, I'm going to use D, comma E is equal to 1 and 12, because 1 plus 12 adds up to 13. And then, say, 3 and, what would that be, 10? Or we could have 5 and 8. And then we could have, say, 6 and 7. You might say, it could be any of these possibilities. We're screwed. Wrong. Why would that be wrong? Because, let's suppose D equals 1 and E equals 12. Then, since D has to be greater than or equal to A, we would have 3 is less than or equal to 1. That does not make the slightest bit of sense. That's nonsense. Here's another reason why. If 1 was one of the data points, we'd have 1, 3, 3, 6, 12. Then the median would be 3. But we're told the median is 6. So that makes no sense. So D cannot be 1. And we can continue this logic so on and so forth. Essentially, our D has to be 6 or higher. D has to be greater than or equal to 6 because D is greater than or equal to C. You might say, why is it greater than or equal to C? You just made that up. No, we didn't, because we said we don't know what the data points are, but we're putting them in order. And just by virtue of that and the logic we have, it's got to be greater than or equal to 6. There's only one option, 6 and 7. You might say, oh, why not 7 and 6? Well, that's the same thing. So, logic tells us that D equals 6 and E equals 7 is the only option. Can't do 8 and 5 because then your median would be 5 and not 6. Same logic holds for all of them. So therefore, D is 6 and E is 7. Now you might have one more question. You might say, hold your horses. You told us the mode was 3. We got 2 6s. We've got a mode of 6. You bamboozled us. Please explain. This is very straightforward. There is also a mode of 6, but the problem simply stated that a mode equals 3. So here I'll put that in red. So, problem didn't lie. You should have all the information, but you didn't need it. Now, going through all this, you might say, okay, that's a lot of logic. My brain hurts. Are you going to do this to us in the test? Yes and no. Yes, you have a logic question. It won't be as hard as these. On the test, what it will be is it'll be a real-world problem. And what I'll do is you will get the mean, the median, the mode, and the range. So it'll be like problem number 1. It'll be like this one. It'll be like that. Very nice, easy, and straightforward. Essentially, the second and third ones, logically speaking, may have been more difficult. It'll be more like the first one, where you get to use all 4. So in this case, what you should do, use the median to find your first data point, then use your mode to find your next 2 data points, then use your range to find your 4th data point, and then use the mean to find the last data point. So to summarize, usually, step 1, A is less than or equal to B, less than or equal to C, less than or equal to blah, 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 less than or equal to N. However many data points you have. Then 2, use the median to find your first data point. In this case, we'll work with odd numbers, keep it nice and easy, because I'm trying to introduce you to the concept of it and show you the applications. And then number 3, if you have it, use the mode to find your next data points. And then 4, if you have it, use the range to find your next data point. And then 5, finally, use the mean/alternate form of the mean formula and if needed, logic to find the last data points. In any problem I give you, you will always have enough information to get your data points out of it. Anyways, that is all we've got for the front part of Chapter 2. Next time, we will go over the back part of Chapter 2. So spend a lot more time on measures of spread, talk about shapes and distributions, so on, so forth. Otherwise, y'all have a great rest of your day.